Okay, this is a formula that needed to be done in the AS level. So for those taking paper 3 and 4 this year that had AS level maybe last year on the other syllabus, then you did not go over this formula. But this is Simpson's Index of Biodiversity. It could be a question you see on your exam tomorrow. But again, you don't need to know the formula. You don't need to know what the variables are. You just need to have practice or know how to go through with it. Okay, so this is going to be looking at the different populations in an ecosystem. We're looking at end crabs. That'll bug me. Um, that's the only one that has it. But or yeah, looking at the different populations of species in a community and trying to identify its biodiversity value, or if it is an area that is rich in biodiversity. Okay. And so this looks at two things, looks for species richness and evenness. And so species richness is the number of species in a community. So, and that kind of like makes sense with its name. If a community is rich, then it has a lot of different species living in it. So the more species in a community, the richer the community is. Remember, a community is all of the populations in a habitat or in an area at the same time. We would say it's all the biotic factors. This also takes into account species evenness. Evenness is going to be like the relative amount or distribution, the abundance of each species. So we can compare population sizes of different species. We wouldn't say a area has evenness if you have 2,000 seagrasses and then just five just five like sea turtles there or something. So it'd be comparing 2,000 within one species to five. That's not very even at all. So we're going to use this data set from a whale fall, where you have the number of species, which is letter N. Oops, that one. Little letter N. And for sharks, we have 2. Amphipods are 8, whales 1, hagfish 1, and then crabs 1. And obviously whales will be 1 because it's a whale fall, so you got 1 dead whale there. The total of all of your species, or all of the organisms in each species, or the total of your populations, another way to say it, is going to be big N. So little n is the amount in each species, and then big N is the total. Again, we have the summation symbol, which is capital letter S in the Greek alphabet. Little letter S looked like this. And then your givens, little n and then big N. First step, if not already done, add up all the individuals to calculate big N. So big N is 15. Step 2, for each species, divide the number of each species, which is N, so the amount in each population, by the total number of all of the species. So you're going to take, for sharks, you're going to do 2, and you're going to divide it by 15. For amphipods, 8 divided by 15. Whales, 1/15. Hagfish, 1/15. And crabs, 3/15. So it'll look something like this. So you're dividing the amount in each species by the total amount there anyways. All right, and then we're going to put that in our results there. And this is another one where I just keep adding this same data set to each different step, and then we're filling it in as we go. But you would just be given one data set in a question. All right, so if you divide 2 by 18, you'll get 0.133. 8 divided by 15, 0.533. 1/15, same for the whales and the hagfish, 0.067. And then the crabs, 3 over 15, 0.200. And 0.2 would be fine, but if we're just going to keep it to the thousandths place, or like to 3 significant digits, although that's not even 3 significant digits. Anyway, step 2's done. All right, now we are going to be looking at the n over big N squared. So the amount in each species divided by all of the organisms there in that community, and then we're going to square it. So take the result from little n over big N from step 2 and then square each result. So there's that result we're looking for. Point 133 squared, 0.018. For the amphipods, 0.533 squared, 0.284. The whale and the hagfish will have the same value. 0.067 squared is 0.004. And then your crabs, 0.2 squared, 0.040. Next step, we got the summation. So calculate the sum of all, again, that's capital letter S in the Greek alphabet, sigma. And this was a lowercase s. All right, add up all the squares or all of the values that you just did from number 3. If you add all of those up, you're going to get 0.350. Last step is the 1 minus that, and you don't have to remember these formulas, you don't have to remember the variables, you just need to be able to follow like the order of operations and be able to execute it. So 1 minus that, you'll have 0.650. All right, so just to identify like what these values can mean, and again, this is looking over the richness, so the amount of different species, and in this example, we had 5 different species there. And then it's evenness, how even they are. And even just looking at it, no, these numbers aren't large at all, but there isn't one that really dominates another. You have one massive food source, the whale, one hagfish, and hagfish are nasty. Like they're just like sink their teeth and face into flesh. Gross. You got a cleanup crew right there with your crabs. You got another cleanup crew with the amphipods and 2 top predators there, which would be the sharks. Okay, so 0.650 from that example. The diversity can range from 0 to 1, where having a low, so being like, I don't know, around a 0 range, would mean that you're going to have low biodiversity. And so obviously having in the higher range, and this is kind of like higher middle. And typically you wouldn't just execute this on just one habitat. You would probably do it for 2 and then compare what different or what habitat is more biodiverse than another. Or it might say like a student concluded that, the rocky shore was more biodiverse than the estuary. Do you agree with this? Or assess the student's findings essentially. And so then you might need to go do the this calculated value for both of them to make that assessment. They did see that on their paper too, actually. All right. So if it's a low biodiversity or it's a low value, then we're going to assume that there's very few successful species in the habitat. And I should say successful. The environment could be extreme or unstable. Remember, extreme is like your hydrothermal vent, but hydrothermal vents are always extreme, so they are also stable. But because they're always extreme, they don't frequently change. Unstable is like your sandy shore because it's porous and it's easily erodible. It's very hard to adapt to those massive changes twice a day. There's going to be few niches or few roles for organisms to occupy. Only few species would be adapted to be in that environment, perhaps. For this one, we know that a whale fall is not going to be a habitat that's going to be something that's consistent. It's not going to be there for a while. It's literally only there for as long as the biomass of the whale is there. And then, the whale fall itself will go through succession. And at each different succession stage, you're going to have organisms coming and going. You can also assume the food webs are going to be simple. And because there's not many species there and there's not many of any species there, there's not many different species, and within those species, there's not a lot of them anyways, then we can assume that there's probably unique situations there. And if there were going to be any kind of environmental change, it would be hard for them to adapt to that. That would most likely bring down the biodiversity. So changing the environment would probably reduce the biodiversity. So hydrothermal vents, sandy shores, even muddy shores. Remember, muddy shores are anoxic. Oftentimes they can be acidic as well. You have a lot of noxious gases there, a lot of sulfurs because of all the anaerobic respiration. Organisms who live in the muddy shore, for example, your mangrove, they're going to have to be able to adapt to that anoxic soil by sticking up some nematophores out of there, like those little snorkels, so that they're able to adapt to that environment. If it's a high biodiversity index, so going to be, the higher range of like 0.5s, and that would even be in the middle. But if it's higher, obviously the highest would be in the 9s. We know there's a greater number of successful species. The habitat is stable, so organisms are able to live there and adapt to it because they're only having to adapt and live in the conditions that they're facing all the time. More niches or more roles will exist, and the environment is less likely to be hostile. There's probably going to be ample amount of sunlight, perhaps a sustainable amount of food. The oxygen there is always going to be available. It won't be under really high pressure. It won't be acidic. The pH won't fluctuate like crazy. So, like in an estuary or even in like a rocky shore tide pool, you can have high fluctuating abiotic conditions. The complex or the food webs are going to be complex because there'll be a lot of organisms there. And if there is an environmental change, it's going to be less likely to damage the biodiversity because you have such an abundance of different species. And within those species, there are numerous amounts of them. So coral reefs and then even rocky shores. Within the rocky shore, things that were able to change a lot, the abiotic factors, would be the tide pools, and those would change twice a day. However, the tide pools also allowed for rocky shores to maintain a pretty high biodiversity because it did mimic some of the marine habitat once the tide went out. All right, and that is the Simpson's Index of Biodiversity. Like I said, most likely this would be comparing two different habitats together to identify which one is more biodiverse than another.